Hi, and welcome once again to day 20 of Just Start Programming, the Rust programming language. Today, I wanted to improve our mini grep program, but unlike the one in the Rust programming book, I tweaked the code a little bit to include the line number where the text was found. So I think I might have complicated things a little bit, but let's see if we can make it work using iterators this time. So join me once again, do it live in one take, no shortcuts, no secrets. Well then, let's just start programming. All right, so here we are once again, improving our IO project. So over here, removing a clone using an iterator. Okay, so previously we have this clone here, and then using the returned iterator directly. What has changed here? Nothing has changed except that here we are passing env args directly. So it says here it won't compile. Passing ownership of the iterator returned from env args to config build directly. Yeah, so here we need to update config build. I think we might have modified this yesterday. Let's see. Let's come back to our source code. Yeah, so mini grep main.rs. Okay, so we open up main.rs. Yep, I think yesterday, not yesterday, the other day we might have added it here. Okay, so that one is done. And then in librs, this time we have iterator string, updating the signature of config build to expect an iterator. Okay, args. Let's check our lib.rs. Did we do it yesterday? String. Okay. Yeah, here it's mutable args impl iterator item equals string. Item equals string. And I think the explanation for item equals string is somewhere here. Okay. We have updated the signature of the config build function, so the parameter args has a generic type with the trait bounds impl iterator item equals string instead of ampersand string. This usage of the impl trait syntax we discussed in traits as parameters. Traits as parameters. Okay. Section of chapter 10 means that args can be any type that implements the iterator. Okay. So args can be any type that implements iterator trait, and it returns string items. Oh, okay. So it returns string items. Because we're taking ownership of args, And we'll be mutating args by iterating over it. We can add the mut keyword into the specification of the args parameter to make it mutable. So that's why mut is added here. Using iterator trait method instead of indexing. So here, we'll fix the body of config build because args implements iterator trait. We know we can call the next method on it. Listing 13-20 updates the code from listing 12-23 to use the next method. There's the next method here. Okay, let's check if we modified that yesterday. Okay, so it's here. Previously, wait, do I have args.next here? Oh, args.next is here. Okay. Query match args.next sum and none. Okay, because next will return option. So option could be sum or none. Then here, file path string match args next. Okay, so this is the query. Next, the next one is the file path. Okay, sum, and then here ignore case for the environment variable. So environment variable is not part of the args. It's in environment variable. Okay, and then we have query, file path, ignore case. So if it's none, it will return the error. Didn't get the query string. Okay, so we can try this out. Terminal, or we can run it from here. The test returned okay, because in the test case I think we haven't modified it yet. So we haven't modified it yet. Okay, and then we wanted to see this one. Can we do cargo? Okay, problem parsing arguments didn't get a query string. So I think here it already stopped. So I did not continue with the next one, args.next, which is for the file path. Okay, so we are going to modify that. So that's the explanation here. Okay, and here making code clearer with iterator adapters. We can also take advantage of iterators in the search function in our IO project, which is reproduced here in listing 13-21, as it was in 12-19. So search, what has changed here, contains query. Okay, so this is from 12-19. So librs, search. Yeah, we have several implementation of search here. So let's just view search. Okay, so this time it looks a bit different. This was from our previous implementation where I introduced vector to contain found. So found is actually a struct having a line number and the content, because we wanted to display the line number where the query was found. Okay, so we need to overhaul this part because in this case we have query here and line is here. Let's compare it to, so this is the original. Here we have contents, contents.lines, then filter, then return collect. Okay, so this part here is the challenge for us. How do we implement filter? Okay, so let's get back to here. Contents, so instead of contents.lines with a for loop, we use an iterator. So last time it returns results. Okay, so let's try this part. Let me comment out. Should still return vect string. In our case, it's vect found. Okay, so this one we have an error because we haven't returned anything yet. And then here, let me uncomment this one. And this one I will comment out. It's just to simplify things so that we are testing search. Okay, so how it was done here, contents.lines. Contents.lines dot filter. So it's a mutable fnmut. So it can be called multiple times and it can be changed multiple times. Okay. Then the predicate would be okay, this one. That would be the line itself. And then line that contains query. Line contains query. Then collect as iterator. So it will be returning that one. Collect. That collect is going to be an iterator cannot be built from an iterator over elements of type str. What can we do here? From the trait from iterator str is not implemented for vectfile. Okay, so we will do something like this. We will not be returning it yet. So we have a collection. Turn it to a relevant. So this part is actually vec of str, and collect would actually create another vector. Okay, so what we can do, I know it's not the ideal one, but we are going to create another vector here. Let me see, vec contents false. It's going to be a collection of str. I think that would be str. Okay, and then but if we do this, we'll miss the line number. We will be missing the line number. Okay, so let me try it step by step. So if we make this into oh, no, not this one. We can put it here. So that it will appear like a function. Then here we can do a print. Let's see. How can we do a count? Oh, count is over here. Okay. So can we do a count? Plus equals 1. So what am I trying to do? First, there should be print line. Can we do this? String literal. Okay. So count equals 1. It's going to be a string literal. And we do something like this. In line number plus issue here. Oh, this is what I wanted to do. Just use count. And here, just count. Yeah. So, going to just fix this first. Can return how do we return the vec? Vec macro. Let's use a vec macro. Then found which is line number and content. Content would be string. Just testing 1, 2, 3. Contents. Type must be known at this point. Okay, so collect. That is that's the original one. Contents. Should be that one. I'll put it here. So here we are returning this. We're just faking it. I just wanted to see the count. Okay. How do we call this again? Cargo run dash dash. 2 and then poem text. So that it printed 1 to 10. Why is it 1 to 10? Because poem contains 10 lines. Maybe let's remove this part. So we only 1 to 9. Let me do it again. 1 to 9. And this one is, of course, this one is fake. So if we do that, it means we can return collect a vector of found. So here, can we do line contains query? Line contains query. If it's true, this is going, line will be added. Can we print the line? So we're line for the time being. Argument never used. double ampersand. Oops. Okay, count and line. Okay, I'm nobody. Who are you? Are you nobody too? Okay, so it means that these things will have it here. Contains query true. It will return mm, returns true. Okay, so it will return true. Can we do something like if, of course, this is true, then I wanted to print this one. What's the error now? Bool found. Okay. Okay, so what we will do is we will return true here or true. Oops. Missing else clause. Okay. Else false. Okay. So it will only print the line number and then the text if it finds it. Okay, so that's the idea. Of course, it's not always the happy scenario, so there's a possibility that it will be false. So if we did not add this in, compiler will complain. Expected boolean found this one. Okay. Or if we did not add this one, if we did not add else, we did not add else, then it will complain that if may be missing an else clause. If expression without else, evaluate to this one. So that's why we need to add else. Okay, so let's run this. There. So now we have 2, are you nobody 2, 6, how dare you to be somebody. So this is the output that we want. Okay. So how do we return that in collect? So if it's true, it will be added. Transforms an iterator into a collection. Can take anything iterable and turn it into a relevant collection. Most basic pattern with collect is used to turn one collection into another. Take a collection, iter on it, do a bunch of transformation, and then collect at the end. Collect can also create instances of types that are not typical collection. For example, string can be built from car and an iterator of result can be collected to here. Okay, so this is what we wanted to do. Because collect is so general, it can cause problems with type inference, such as this one. All the few times you see the syntax affectionately known as the turbo fish. This helps the inference algorithm understand specifically which collection you're trying to collect into. Turbo fish. Okay, so it's something interesting. Back the queue. But what if I have my own vector? So collect colon vector of this one. If you have a list of results, yes, you can use collect to see if any of them failed. Okay, partial hint with a turbo fish. So it would look like this. If we specify, how do we do that? How do we do that one? Okay, because the count is already done here. We are returning true. Does it mean that vec contents will contain this one? Maybe not. Okay, so let's try for line in vec contents. Vec contents and then print line. We put something like that. So this one is not part of any syntax, it's just a marker. Backslash t is tab. What is this line? This one will be count. Yeah, but count is already used over there. Let's try this one first and see what it looks like. Yeah, so it's only the text. It's only the text. Why it's only the text? Because of this. If we put something like does that? Where did I see that one from collect? Like this, vector of found. Okay, now so it will complain. Expected struct, found. Yeah, cannot build from an iterator of elements of type str. Type str. So, okay. Let's get this one first. And this one will change it to found. Because lines contents. Okay, because originally contents is like this. How did we do it last time? Search. Contents is also str. And then we are returning vec found. Found is here. Okay, let's think. Think. Let's keep it as it is. So what can we do here? We have the line, the contents. We have the content, but we need the line. Where can we put the line? Line number, the line number. We are filtering. Lines will return. Yeah. Lines will return. This one will return to our false, but how can we after the filter, okay, so filter creates an iterator which uses a closure. Return the iterator will yield only the elements for which a closure returns true. Will yield only the elements for which the closure returns true. will yield only the elements. Okay, so if this is true, can I do something like found here? Found. No. My number. Count. Content. Line. 2. No, just do a 2 string. Well, we just created the found, but I don't think it will be inside collect. Yeah, because it's still vector of that one. So we need filter to return struct found. Contents lines over a line of string slices. Okay, we know that it's a line of string. And then inside the line of string, we are checking if the line contains query. If it contains, it's like this. Collect me from iterator. Transforms an iterator into a collection. Collect can take anything iterable and turn into a relevant collection. Is used to turn one collection to another. Yeah, this is what we wanted to do. Turn one collection into another. Take a collection, call iter on it, do a bunch of transformation, and then collect at the end. Collect can also create instances of types that are not typical collections. For example, a string can be built from car, cars, and an iterator of result collection. Result collection of T. And then you have E. Oh, because collect is so general, it causes problem. Result TE. So car is T, perhaps. E, what's E again? I think E is error. So it means, can we do return result? Oops. collection T. Collection of T, so found. And then here, what can we add here? E. I don't know how to do that. Can we do here? Iterate or filter? Okay, maybe let's search. Rust programming language filter custom iterator struct. Let's see if we get anything. Oh, AI struct. Yeah, I know that it's that one. Where's the filter? Filter in custom iterator. What's in here? Let's see. Iterator item plus car. Item equals token and then create your lexer. Oh, item equals token. Item equals token. Where do we have that one? IMPL iterator item string. Okay, so does it mean here filter instead of line like this? We can have contents, select contents, select this one, IMPL iterator. Item equals vec. Put it here. Found. Vec found equals contents lines. It's the issue here. Only allowed in arguments and return types of functions and methods. Okay, it means can we do it here? MPL IMPL trade is not allowed in closure parameters. IMPL trade is only allowed in arguments and return types of functions. Okay, so we cannot do it here. So we are stuck with string. We're stuck with that. What can we do? Can only return true. Collect. Okay, how about if we will not force that issue? Expected type. Okay. Can this. Can remove this also. What? Run that one first. Okay. Let's find another solution. So back contents will have this. Let's bring it back. I don't have any elegant solution yet. So let's try to see some workaround. It will print that one. Yeah, but what will happen to count? I will create another mat. Line index. Maybe I put it vec line. Put vec line number. Line number equals to vec It's unknown. Okay, so it's unknown. Vect line number, and then here, if it is found, then I will add it in. Yeah, so let me cheat a little bit. Push count. So I'm going to store it in vect line number, and then here what I'm going to do is uh, let me think. Let me print this one first. Okay, 2 and 6, and this one doesn't have a line number. Okay, so it is going to be the line. Let me change that. I'll put that as 1, and here I'm going to create the real line number, slash t to separate it, and then here we get vect line number dot next. Let's make use of next. Okay, anyway, I think if we find anything, so the line is count here, and we're going to push that value here, so it's the same as 2, and then this one is already here in vec contents. So all we have to do is, when we get one of the contents, we display it here, and at the same time in our vect line number we retrieve the next value. Yeah, so I think that should work. Let's try to print it out. I know it's not that elegant, but it should work. Oops. What's the issue? What is this? No method named next found. Okay. I think it should be what? Iter function dot next. No, that's the iterator again. Iter dot next. Should be like that. That's the issue. Option at integer doesn't implement. Okay. Informal strings you will be able to use. Okay, so because it's an option, can we do something like this? Oh, no. Only put one. It showed something, some number 2, some number 2. 2, 6. Returns the iterator over the slice. The iterator yields all items from start to end. From start to end. Okay, this is from start to end. Ah, okay, okay. So we need to do something. Let not iter vec 9 num equals to vec 9 number dot iter. Oh, but it looks the same. It looks the same. So now we have sum 2 and sum 6. Okay, but we don't want sum. We don't want sum, so how do we return 2? This is sum, so if it's sum, we do something like this. So, this is option. Okay. Now, it is going to be sum. It is like this. Okay. And return next sum. So can we enclose it in sum? Can we enclose it in sum? Sum. This. So then this becomes just number. Display. Oh, now it becomes sum. That's not what I want. I think I did not learn anything from the previous chapters. Let me think. Let me think. I know that it's there. Next. How do we retrieve the value of option again? How to extract the value from option? Yeah, it's sum and none. Okay, but sum 42. I don't want to use match. Oh, you can do something like this. If let, okay. The question mark operator. This operator is used in functions that return option or result to propagate none or error values early. The option is sum, the inner value is unwrapped. Otherwise, it's returned, none is returned from the current function. Returns none if S is none. So if you just put question mark, question mark, use question mark here also. Unwrap. Oh, okay, okay. There you go. Unwrap. Unwrap. Unwrap else. So unwrap or unwrap else. Okay, unwrap. So now that should be a number. Yes. So once we have a number, then in our vector, what is our return vector? Results. So here we can substitute results that push found line number colon either vec line number next that unwrap comma, then the other one is content, then this line. Oh, it looks confusing. Line is actually the text, then this thing here is the line number. Let me just comment this out. Oh, what's the issue? Line is to string to string. Unwrap is found integer. Consider dereferencing the borrow. dereferencing the bar. Okay, let's follow that one. Dereferencing. So oh, correct. Correct. And this one we don't need this anymore. We comment out results. There. Then you run. 2, 6, 2 and 6 results. So we did not print anything here. Let me comment this out. So where is found? Where is this found? Where is it coming from? Ah, from here. So there you go. It's not an elegant solution, but it worked. Yeah, maybe we can improve this further once we learn more concepts in Rust. For sure, there's a better way of doing it. Because what I wanted to do here is instead of string slice, string str, collect should be able to return vec found directly so that we don't need to do these lines. Yeah. Okay. Anyway, that worked. So what we can do is just to copy exactly the same pattern for search case insensitive. Yeah, so it should be, yeah, here should be similar. Can do the same approach. All right, so let me save this and keep it here. I think in the somewhere for sure we will be reusing that. Okay, so I hope you guys have learned something as well. I know those things are not in the book, but somehow we managed to wiggle our way through. I'm sure this is not the only solution, so if you have a better one, please send me a comment as well. So and then in the next sessions we can go through it together here live as well. Yeah. Okay, moving on. Let's take a look at this one. Comparing performance loops versus iterators. So which one is much more faster? Okay, so it says here, to determine whether to use loops or iterators, you need to know which implementation is faster. The version of the search function with an explicit for loop or the version with iterators. We ran a benchmark by loading the entire contents of The Adventures of Sherlock Holmes by Sir Arthur Conan Doyle to a string. Yeah, so this is a book. To a string and looking for the word in the contents. Here are the results of the benchmark on the version of search using for loop and version using iterators. Let's see, test bench search for bench. Is it searching for bench? Plus minus. Two implementations have similar performance. We won't explain the benchmark code here. Because the point is not to prove that the two versions are equivalent, but to get a general sense of how these two implementations compare performance-wise. Similar. Is it referring to this one? Yeah, so there's a slight difference here. Okay. For a more comprehensive benchmark, you should check using various text of various sizes as contents, different words and words of different lengths as the query, and all kinds of other variations. The point is this: iterators, although a high-level abstraction, get compiled down to roughly the same code as you'd written the lower-level code yourself. Iterators are one of Rust's zero-cost abstractions, by which we mean that using the abstraction imposes no additional runtime overhead. This is analogous to how Bjorn Strostrup, the original designer implementer of C++, defines zero overhead in foundations of C++. Oh, that's nice. In general, C++ implementations obey the zero overhead principle. What you don't use, you don't pay for. And further, what you do use, you couldn't hand code any better. As another example, the following code is taken from an audio decoder. The decoding algorithm uses the line prediction mathematical operation to estimate future values based on a linear function of the previous samples. This code uses an iterator chain to do some math on three variables in scope: a buffer slice of data, an array of 12 coefficients, and an amount by which to shift data in. Okay, what is this all about? We've declared the variables within this example but not given any values. Although this code doesn't have much meaning outside of its context, still a concise real-world example of how Rust translates high-level ideas to low-level code. What's in here? Buffer reference to a mutable array of I32. Okay. So it seems like here you have an iterator and then you have a zip function. You're doing something here and then you're doing a map and then you're doing a sum. Oh, sum colon. This is our clue. This one looks like it returns what? I64 in the end. Prediction. Maybe this is our clue to a vector of found. Okay, to calculate the value of prediction, this code iterates through each of the 12 values in the coefficient. 12 values in the, okay, here, 12 values in coefficients, and uses the zip method to pair the coefficient values with the previous 12 values in the buffer. Then for each pair, we multiply the values together, sum all the results, and shift the bits in sum. Okay. I don't understand this, honestly. I hope you guys can understand this, but at my level, at the moment, I really don't understand this. But let's continue to read and see what else is here. Calculations in applications like audio decoders often prioritize performance most highly. Here we are creating an iterator using two adapters, then consuming the value. What assembly code would this Rust code compile to? Well, as of this writing, it compiles down to the same assembly you'd write by hand. There is no loop at all corresponding to the iteration over the values in coefficients. Rust knows that there are 12 iterations, so it unrolls the loop. Unrolling is an optimization that removes the overhead of the loop controlling code and instead generates repetitive code for each iteration of the loop. Removes overhead of the loop controlling code and instead generates repetitive code for each iteration of the loop. All of the coefficients get stored in registers, which means accessing the values is very fast. There are no bound checks on the array access at runtime. All these optimizations that Rust is able to apply make the resultant code extremely efficient. Now that you know this, you can use iterators and closures without fear. They make code seem like it's higher level but don't impose a runtime performance penalty for doing so. Great. So we should use iterator then. Yeah. And closures. Yes. Summary. Closures and iterators are Rust features inspired by functional programming language ideas. They contribute to Rust's capability to clearly express high-level ideas at low-level performance. The implementations of closures and iterators are such that runtime performance is not affected. This is part of Rust's goal to strive to provide a zero-cost abstractions. Okay. Now that we have improved the expressiveness of our I/O project, let's look at some more features of Cargo that will help us share the project with the world. Oh, okay. So the next topic is the advanced level of Cargo and crates. Okay. So we managed to do this, but in the end, there's a for loop here, which is not the ideal one, because what we're trying to do is we replace for loop with iterators. Or maybe we can transform this later on into another iterator kind of approach. Okay, let me end here, and on the next day we'll cover Cargo and crates. Hopefully this will fit into our one day lesson. It looks long, but let's see. Install. Okay, so I think we can cover this tomorrow or the next day. All right, thank you so much for accompanying me learning Rust programming language. And before I finally end, let me thank my supporters.